Hi, everybody, and welcome back to Hanson Math YouTube video tutorials. Today's lesson regards the conic section known as the hyperbola. Let's get started and let's take a look. Remember that the conic sections they come from slices of a cone. So here we have a double cone, and I can move the slice around, and you can notice that I'm slicing parallel to the base. So we have circular cross sections. Now, if we take our cross sections and we put them on more of a oblique or a slanted cut, you see at the cross section switches from circular to oval or elliptical in nature. That was the one that we studied prior. Now, what we're going to do today is we're going to change the slice such that the slice is like this, where you're going vertically through both cones. And you can see here on the screen that you have two branches, and these branches form the hyperbola. So this shape is the hyperbola with these two branches. I can move it around a little bit. You can see how it changes shape depending on where we are on the cone. I could also play around with the angle. We could do lots of stuff like this, move it around. So again, the hyperbola comes from slicing through such that you go all the way through both cones through their base. Now, your textbook will say that a hyperbola is the set of all points x, y, in a plane which the difference of whose distances from two fixed points called the foci is a positive constant. So now, instead of the ellipse where it was the sum of the distances from the foci, now it's the difference. So if you look at this point P here, that is in pink, as I move it around the branch, you'll notice that these distances from the two foci points here and here, those individual distances change. But you can see that when you subtract them, which is PA minus PB right here, it's a constant 2. Now, it's not always 2. 2 is just the size of this hyperbola. But you can see that those individual distances from the foci to this point P change. The difference or the subtraction of those two lengths remains the same, no matter where you are on the hyperbolic curve. Now you're looking at our class notes, which gives you the definition of a hyperbola, which I've already cited, and it shows you the cross section here in orange of the double cone being sliced. And without further ado, we're going to get right into it here and start working on some of the particulars of the hyperbola. So let me bring up my writing device here and we'll get started. Okay, in this picture, you can see the two hyperbolic branches in red, and these points in blue are the foci, and we'll go through everything, in the coming time here. So the first thing let's talk about is the orientation. The orientation of a hyperbola can either be horizontal or vertical. You can see here that these branches are going left and right. So the orientation of this particular example would be horizontal. We'll look at a vertical example coming up in a little bit. The vertices are it's the point on each branch where these curves kind of bottom out. So the vertices here would be right there and right there. And if we let's take the notes here. So we're going to say that the vertices are the point on each branch. I call it where the curve bottoms out. You have to excuse my handwriting. I can barely write as it is, let alone with this stylus. Okay, point on each branch where the curve bottoms out. So if we call this one, let's call this one vertex 1. So its coordinates would be -5, -1. And if we call this one vertex 2, its coordinates would be 3, -1. Okay, remember, the beauty of this video is you can pause, you can rewind, you can even fast forward, you can make it your own. Okay, the next thing we'll talk about here is something called the transverse axis. The transverse axis is the axis that connects the vertices. Okay, it's an imaginary axis that connects the vertices. So if I draw it in here, it would be this path. That's called the transverse axis. So again, we're going to put it's the axis that connects the vertices. Okay. The length of the transverse axis, LENGTH, is what's known as 2A. All right. So if we look at this particular example here, we can see that this transverse axis has a length of 1, 2, 3, 4, 5, 6, 7, 8. So 2A, the whole thing is worth 8. So therefore, A is worth 4. And we'll get into where that 4 is used and where that's coming from in just a bit as we go. Okay, in fact, that's a good segue. That leads us into the center. The center is the point in the middle of this transverse axis. So the center is in the middle. Actually, let me change colors. Let's see, let's go light blue. The center is in the middle of the transverse axis. Okay, so we're smack dab in the middle. 1, 2, 3, 4. We're right here. So that's the center. So let's see, point in the middle of the transverse axis. It's also in between the vertices. It's called HK, which is the same as all of the conic sections center. And the example in this case is this point right here is at, from the origin, left 1, down 1. So its coordinates are -1, -1. Now, notice that that A value, that A equals 4, you can see here from the center, it's 1, 2, 3, 4 units to the right to hit this vertex. And it's 1, 2, 3, 4 paces to the left to hit that vertex. Okay, so that's another thing that this A value is telling you, the distance from the center to either vertex. All right, next, let's get into those special points called the foci. The foci are special points. They're always inside of each branch. So here, they're inside of the curve. You can see that I already have them as blue points here and here. So we'll call this one focus 1, and we'll call this one focus 2. It doesn't matter which one's 1 or 2. I'm just differentiating them. And you know, we already been through the definition here. That's what really makes this thing tick. So if I were to plot a point anywhere on this branch, let's say right here, and if I were to take the distance from this focus to that point and this focus to that point and subtract those two yellow lengths, I'm going to get a number. And then if I were to go somewhere else on the curve, let's say here, and I take this distance and I take this distance, these two yellow distances, and I take the length and subtract them, I get the same constant number. So that's what makes this hyperbola tick. Okay, so let's see where we're at. There's special points inside each branch. So we can write that down. There's special points inside each branch. All right. So, for example, in this particular problem, the first focus point, foci is plural, is right here. So that is at -6, -1. And the second one is at 4, -1. All right. What else can we say about these things? Well, we can say that the distance from the center to either focus point or the foci plural is what's called C. So in this particular example here, all right, let's see, from the center to either focus, it would be 1, 2, 3, 4, 5 paces, or from this one, 1, 2, 3, 4, 5. So C equals 5 in this particular example. All right. So let me now work with you on something called the conjugate axis. The conjugate axis is an axis that is perpendicular to the transverse axis. So it's an invisible axis that's perpendicular to the transverse axis. Okay. And it goes through the center. Okay, so it's perpendicular to transverse axis through the center. Pardon me, I just adjusted my screen a little bit. The conjugate axis is perpendicular to the transverse axis, and it goes through the center. All right. And its length is said to be 2b. Okay. So in this example, well, how do we know what 2b is? Well, we'll get to it in just a second. The formula that relates a, b, and c for the hyperbola is c squared equals a squared plus b squared. It's different than the ellipse. The ellipse was minus in the middle. The hyperbola is plus. So in this example, we had the center to focus distance was c. So that would be, in this particular example, 5 squared. Let's see, a was the distance from the center to each vertex. We already discussed that was 4. And then b squared, okay, we don't know what that is. So now we will solve this equation for b, and we'll be well on our way here. So we have 25 equals 16 plus b squared. Subtract 16 to both sides. So we get 9 equals b squared. You can see where this is going, I think. Take the square root. So 3 equals b. So if the entire length of this conjugate axis is 2b, then in this example, it would be twice 3, or a length of 6. So it would be 3 each way from the center. So it would be 3 up. Remember, because it's perpendicular, it makes like a plus sign from your transverse axis. So it's going to be 3 up for an endpoint, and then 3 down. You can see that if I draw it in, that has a total length of 6. Okay, so we are moving along really good right now. What I would like to do is now we can work on the equation of this particular hyperbola. So we're going to start with the center, which is very much like the other conic sections. We have HK. So since our center was -1, -1, you do the opposite signs. So it's +1, plus 1, it still equals 1. You have your fractions, and there's a minus sign in the middle. The ellipse had a plus, the hyperbola has a minus. Here is the a squared value. Okay, the a squared value is always going to come in the first fraction. So a was 4, so 4 squared is 16. This is the a squared value. And the b squared value always goes here. B was 3, so 3 squared is 9. And there is your equation of a hyperbola. Things to note is that you still have equal to this constant 1. There is a subtraction sign in the middle. A squared always comes in the first fraction, and the orientation is told by whichever variable is in the first fraction. So since this one is x is in the first fraction, x is horizontal. If y would have been here, it would be vertical, which you will see in a minute. Okay, the last thing we're going to do here is the equation of the asymptotes. The asymptotes are imaginary lines that kind of frame in, or they kind of bound this hyperbola. So let's do the following here. If you take this transverse and conjugate axis, and if you kind of square it off like so, and then do what I call draw an X box, which is through the corners of the box, through the center, through the opposite corner, and then do the same thing on the other side. It's an imaginary line through the corner of this rectangle, through the center, out through the other corner. Notice that that kind of is like a fence, and it kind of helps to kind of hold in the curve or give the hyperbolic branches their shape. So these are two linear equations. They're two lines. One line has a positive slope, rising. The other one's falling. So to get them, we do the following. The equation is y equals k plus or minus b over a parentheses x minus h. And now it's a pretty easy plug and chug. Again, this is just linear equations. Y equals, our k value was -1. That was coming from the center. So we've got -1 plus or minus. We know b and a. B was 3 over a, which was 4, parentheses x minus h. Well, h is here. That's the x component of your center. So the opposite of -1 is +1. There is no need to take it any further. You could distribute and whatnot to make it look like y equals mx plus b, but there is no need. So this was an exploratory example of all of the particulars of the hyperbola. Now we're going to further dissect an example of horizontal orientation and vertical orientation, and then wrap up this video for the day. Here in the blue box, we have some information about the standard form of the equation of a hyperbola. Rather, if it's horizontal or vertical, you can pause and read this if you like. It's also available on my note sheet. And we're just going to keep it moving right along here. Example 1, we have a hyperbola. Note that we have a minus in between the two fractions. That's one of the ways to spot it, to make sure that we're not talking about the ellipse. So I have a blank graph here, just like you do. So here is how we will graph this. Okay. The first thing I'd note before I do anything, though, is in this fraction, in this first fraction here, this is an x fraction. X tells you that the orientation is horizontal, okay? So if x comes first, it's horizontal. It has nothing to do with the denominators being bigger, nothing like that. If the x is in the first fraction, it is horizontal. Okay? So step one is we are going to plot the center. Okay? The center is HK. It's the opposite of what you see in parentheses. I don't see any number in parentheses here, so that means that we have a 0 for the x component, and then the opposite of the y information, the opposite of -1, is a +1. So our center is at 0, 1, which I will plot right here. Big, beautiful center at 0, 1. Okay, that's step one. Step two is that a squared is always the first denominator. So it's this one. It has nothing to do with size. The first fraction, that's your a squared denominator. So a squared is always the first denominator. All right. So in this one, we have a squared is equal to 16. So if you take the square root, that implies that a is equal to 4. And again, since this one is attached to x, it's going to be horizontal. So if we start at that center and we go 4 units horizontal, so that'd be 4 to the left, 1, 2, 3, 4, plot a point. 1, 2, 3, 4 to the right, plot another point. That is going to give you the vertices. So you're going to have one here and one here. Okay? So if you want to take note of that, we can. The location of the vertices is going to be at -4, 1. And the other one is at 4, 1. All right, perfect. Now, the vertices, that's where the curves kind of bottom out, or that's where they branch from. So that's important to keep in mind. Okay? The vertices, remember, they're on the transverse axis. All right, step 3. Step 3 is to note that b squared is the second denominator, or the one further to the right. So in this case, b squared is 4, which implies if you take the square root that b equals 2. And notice that that one was attached to the y fraction. Y stuff is vertical. So that's the vertical endpoints from the center. That gives you that conjugate axis. So if I switch colors here, from the center, I'm going to go 2 units up, 1, 2, plot a big, beautiful point, and then 2 units down from the center, plot another point. All right. That is going to give us the endpoints of the conjugate axis, which is going to help lead us into step 4. Step 4 is what I call drawing an X box. It's not as fun as the video game system, but it gets the job done here. So to draw this X box, what you're going to do is you're going to take the endpoints of this conjugate axis, and you're going to box in all the way to the vertices and across and up and over. Okay? So instead of having a plus sign, you're framing it in like that. What that will allow you to do is that will allow you to sketch the asymptotes. So draw the X box, sketch the asymptotes, which are the imaginary diagonal lines that kind of frame the hyperbola in. They go through the corner of this rectangular box, through the center, out the other corner. Okay? So what that is going to allow us to do now is draw the X box, sketch the asymptotes, and now we can draw in the branches. okay? The branches always start from the vertex and then they go towards the asymptote, although they never touch it. Again, it's kind of like a fence, kind of gives it its shape. And the same thing on the right side, something like that, okay? Looks pretty good. Excuse me. So that was step 4. We can also do the equation of the asymptotes. So we'd have y equals k, which was here, 1 plus or minus b over a. So b is, I'm going to write it underneath here. It's y equals k plus or minus b over a. So let's see, that would be 2 over 4 times x minus h. So h here is 0, so I'm not going to put minus 0. That doesn't do anything. So that is basically it. We can simplify a little bit here. We have y equals 1 plus or minus 2/4 is 1/2 x. That is the equation of the linear asymptote lines, diagonal lines. So we've got that. We sketched in the branches, we're good. Last step is to put in the foci. That'll be step 5. Remember, the foci related to the equation, c squared equals a squared plus b squared. Plug in what we know. We do not know c squared. A squared was the first denominator, 16, plus b squared, which is the second denominator, 4. So we get c squared equals 20. Take the square root of both sides. C equals the square root of 20. Remember, 20 is containing a perfect square. It's root 4 times root 5. 4 is the perfect one. The square root of 4 is a whole 2. So 2 root 5. That is the distance from the center inside each branch, which I will show you in just a second. I'd encourage you to use your calculator. 2 times the square root of 5 is very approximately 4.5. So if you start from the center and move 4.5 to the left, 1, 2, 3, 4.5, now you are inside the curve. So that's one of the focus points. So its location would be negative 4.5, comma 1, and its buddy would be to the right, 1, 2, 3, 4.5. So it would be positive 4.5, comma 1. I think that does it, but the only thing I want to do here is let me back up. I really don't remember. See, I just fooled myself. 4.5 is a very, very rounded off. That's just so we can sketch it in the picture. I got to remind us that we want to use radical or exact values in our answers. So let's go over that a little bit again. So I said negative 4.5, comma 1. Remember that 4.5 is very approximate for 2 root 5. So it's actually 2 root 5, comma 1. That one's to the right, and the one that's to the left is negative 2 root 5, comma 1. However, I do think it is useful to think in terms of the decimal, just so you can know how far to walk it to put it into your sketch. When I think of 2 root 5 without my calculator, I don't really think of that as 4.5, but that's just me. And again, it's really 4.4721. This is extremely rounded off. Okay, I hope this helps. Thank you for sticking with me. This was an example of a horizontally oriented hyperbola. Let's look at a vertical one, and then we're going to take this video home. Last but not least, let's look at an example of a vertical hyperbola and what that would entail. So what we'll do first is the following. The most important thing to note on here is that you are looking at a vertical hyperbola and why we're doing that. So let's focus in on the first fraction here. If the first fraction, the leftmost fraction, has the y variable, that is your tip-off immediately that the orientation of this hyperbola is vertical. So if you're planning ahead, it's going to look something like this with an upward branch and a downward branch. Okay? Once you have the orientation correct, that's gotten by the first fraction, you want to plot the center. Now, remember, the center in terms of a formula is HK. H is the coordinate after the X, K is the coordinate after the Y. Now, this is where most students make a mistake. You get really excited. You say, all right, I see you here, 1. But no, this 1 is attached to the Y variable. You actually need to start over here with the X parenthesis, and you take opposites. I know you see a +2, but the opposite sign for H is -2, and then the opposite of this -1 here on the Y is +1. So that is the center of this hyperbola. It is left 2, up 1, plot a big, beautiful center. Okay, now that will lead us into step 2, which is to plot the transverse axis dimensions, if you will, to get the vertices. So let me switch colors here, if I can. There's always some kind of a technical difficulty here. Oh, there it is. Okay, so step 2 is to take the a squared value, which is always on the first fraction. So we have a squared here is equal to 4. If you take the square root, that implies that a is equal to 2. Again, this is on the y fraction, so it's vertical. So you're going to go up and down 2 units from the center. So if you go up 2 units, plot that. That is your vertex, one of them. From the center, go down 2 units and plot the other vertex. So you're going to have one branch going up, one branch going down. If you were to connect those vertices, that is the transverse axis, which would be a grand total of 4. Okay, we got that. Now we'll move on to step 3. Step 3 is to deal with the b squared. So b squared is the second denominator, which is 9. Square root that sucker, and you get b equals 3. And since it's attached to the x fraction, x stuff is horizontal or right, left from the center. So from the center, we're going to go left 3, 1, 2, 3, plot an endpoint, right 3, 1, 2, 3. Okay, if you were to connect those orange points, that would be your conjugate axis, which would be a length of 6. All right. Next, we're going to put in the X box and sketch the asymptotes. So let me switch colors again. All right. Step 4, we're going to put in the X box. So again, you're framing in these vertices and these endpoints of the conjugate axis. All right. We're going to put the asymptotes in through the corners of the box, through the center, the best I can freehand here. Do that to the other corner of the box, through the center, boom, like that. So those were the asymptotes. I always thought it was kind of an unusual word. And now we can work on the equation of the asymptotes. So for a vertical hyperbola, it's going to be y equals k plus or minus a over b parentheses x minus h. Now, if you've watched my videos, you can tell I'm not a big formula guy. I don't like to memorize this stuff, so I'd rather think about how it works. So I don't really think about a over b because the horizontal ones are b over a. So to not even have to think about that, here's what you do, all right? Y equals, your K value is your Y coordinate from the center, so that's 1. Plus and minus, don't even worry about this A over B. This is just the slope, or rise over run. And you can get it by starting at the center and going rise, up, and then run over to the corner of the rectangle of the X box. So for this one, from the center, you go up 2 over 3. So that is your slope, or your fraction there. So you don't really even need to think about A over B. And this works for the horizontal ones too. Just start at the center and go rise and then run to the upper right corner of the X box, and that will be correct. Parentheses, X, the opposite of H. H here from the center was a -2, so the opposite of that is +2. That is the equation of the asymptotes. All right. Let's see. One other thing we can do is I can go back. We can put in the coordinates or the vertices if we need to write that down. So the vertices, you have, remember we had one here that was -2, 3. And the other one is -2, -1. Since we're documenting all of this, I think the only thing we're missing here is our branches. Got to put those in. This is vertical, so it starts from the one of the vertices here. Again, you get really close to your asymptotes. It never touches them, even though it's really impossible to draw it that way. And the other one like that. All right. Again, the asymptotes, they act like a fence to kind of give it its shape or its bound. And next, so that was step 5. That was sketching the branches. And step 6, we'll work on putting in the foci and their coordinates. So they're related by c² equals a² plus b². So we have c² equals a² was our 4, b² was our 9. So we have c² equals 13, square root of both sides. C equals square root of 13, which we'll use as our coordinates. But to help us plot this, it's helpful to take the decimal. The square root of 13 is approximately, well, let's see. Oh, good old square root of 13. You are 3.6. So that means we have to start at the center of the picture here and walk 1, 2, 3, and 0.6 into the branch. So that's one focus point. Then start at the center and go down 1, 2, 3, and the 0.6. So we'd be right there. That's the other focus point. All right. But in terms of the coordinates, we have, well, we went left 2, right? Everything is on this kind of -2 line. So that's our x coordinate, comma. So for the y coordinate, we were starting from the center, which was this 1, and then we went up a distance of the c plus up root 13. And then for the other one, it's left 2, starting at a height of 1, which was from the center point, but then we went down that 3.6 down, which is minus, and that's root 13 to be precise and not round. These are exact values. All right, I think that does it. That is our vertical hyperbola. Before I log out here, the only thing else I want to say to people out there in math land, if you see a hyperbola equation that doesn't have a denominator, like for example, if this 9 wasn't here, you can always create a denominator by putting it over 1, and you'd go from there. So if you do not have a fraction, you can create one by putting over 1. I think that does it. Thank you very much. As always, it's a great day to be a pioneer, and I hope this finds everybody well. Take care.